formula to calculate grounding conductor size based on NEC section 250.122 involves several steps. Firstly, determine the feeder current. Find the total amperage of the load that the feeder will be supplying. Secondly, calculate the hot conductor area. Calculate the total cross-sectional area of the hot conductors in circular mills. The formula for this is hot conductor area equals number of hot conductors multiplied by cross-sectional area of each hot conductor. Thirdly, compare to 1100 kc mil. If the total hot conductor area is greater than 1100 kc mil, proceed to the fourth step. Otherwise, skip to the fifth step. Fourthly, calculate grounding conductor area for hot conductor area greater than 1100 kc mil. The grounding conductor area equals 0.125 multiplied by hot conductor area. Fifthly, calculate grounding conductor area for hot conductor area less than or equal to 1100 kc mil. Grounding conductor area equals 12.5% multiplied by hot conductor area. Sixthly, round up to standard size. Round up the calculated grounding conductor area to the next standard conductor size available. There are some additional notes to consider. The grounding conductor size should not be smaller than the circuit conductor size. If multiple sets of conductors are used, calculate the grounding conductor area for each set and use the largest calculated value. The grounding conductor can be a single conductor or multiple parallel conductors. The green color of the grounding conductor is only a requirement for specific applications, such as equipment grounding. To further illustrate these calculations, let's consider some examples. Example 1: a feeder supplies a load of 800 amps. The feeder consists of 3 500 kc mil copper conductors per phase. Firstly, determine the feeder current. The feeder current is given as 800 amps. Secondly, calculate the hot conductor area. The hot conductor area is 3 conductors multiplied by 500 kc mil per conductor, which equals 1500 kc mil. Thirdly, compare to 1100 kc mil. Since 1500 kc mil is greater than 1100 kc mil, proceed to step 4. Fourthly, calculate grounding conductor area. The grounding conductor area is 0.125 multiplied by 1500 kc mil, which equals 187.5 kc mil. Fifthly, round up to standard size. Rounding up 187.5 kc mil to the next standard conductor size, we find that a 4/0 copper conductor which has a cross-sectional area of 211.6 kc mil would be appropriate. In this case, a 4/0 copper conductor would be required for the grounding conductor. Example 2: a feeder supplies a load of 400 amps. The feeder consists of 2 3/0 aluminum conductors per phase. Firstly, determine the feeder current. The feeder current is given as 400 amps. Secondly, calculate the hot conductor area. The hot conductor area is 2 conductors multiplied by 262.4 kc mil per conductor, which equals 524.8 kc mil. Thirdly, compare to 1100 kc mil. Since 524.8 kc mil is less than 1100 kc mil, proceed to step 5. Fifthly, calculate grounding conductor area. The grounding conductor area is 12.5% multiplied by 524.8 kc mil, which equals 65.6 kc mil. Sixthly, round up to standard size. Rounding up 65.6 kc mil to the next standard conductor size, we find that a number 4 aluminum conductor which has a cross-sectional area of 66.36 kc mil would be appropriate. In this case, a number 4 aluminum conductor would be required for the grounding conductor. Example 3: a feeder supplies a load of 1200 amps. The feeder consists of 4 350 kc mil copper conductors per phase. Firstly, determine the feeder current. The feeder current is given as 1200 amps. Secondly, calculate the hot conductor area. The hot conductor area is 4 conductors multiplied by 350 kc mil per conductor, which equals 1400 kc mil. Thirdly, compare to 1100 kc mil. Since 1400 kc mil is greater than 1100 kc mil, proceed to step 4. Fourthly, calculate grounding conductor area. The grounding conductor area is 0.125 multiplied by 1400 kc mil, which equals 175 kc mil. Fifthly, round up to standard size. Rounding up 175 kc mil to the next standard conductor size, we find that a 3/0 copper conductor which has a cross-sectional area of 167.8 kc mil is slightly below the calculated value. Therefore, we must use a 4/0 copper conductor which has a cross-sectional area of 211.6 kc mil. In this case, a 4/0 copper conductor would be required for the grounding conductor. Keep in mind that these calculations provide the minimum required size for the grounding conductor. In some situations, it may be necessary to increase the size of the grounding conductor to ensure adequate protection. In summary, calculating the grounding conductor size according to NEC section 250.122 involves determining the feeder current, calculating the hot conductor area, comparing it to 1100 kc mil, and then using the appropriate formula to calculate the grounding conductor area. Finally, round up to the next standard conductor size. Remember to always consult the latest edition of the NEC and consult with the qualified electrical engineer to ensure compliance with all applicable codes and standards. It is important to note that there are other considerations in addition to NEC section 250.122 that may affect the size of the grounding conductor. These include, but are not limited to, voltage drop, fault current, and coordination with overcurrent protective devices. Always refer to the applicable codes and standards and consult with a qualified electrical engineer to determine the appropriate size of the grounding conductor for a specific application. Let's look at some common conductor sizes and their corresponding circular mil area. Number 14, AWG has a circular mil area of 4,107 circular mils. Number 12, AWG has a circular mil area of 6,530 circular mils. Number 10, AWG has a circular mil area of 10,380 circular mils. Number 8, AWG has a circular mil area of 16,510 circular mils. Number 6, AWG has a circular mil area of 26,240 circular mils. Number 4, AWG has a circular mil area of 41,740 circular mils. Number 3, AWG has a circular mil area of 52,620 circular mils. Number 2, AWG has a circular mil area of 66,360 circular mils. Number 1, AWG has a circular mil area of 83,690 circular mils. Number 1/0 AWG has a circular mil area of 105,600 circular mils. Number 2/0 AWG has a circular mil area of 133,100 circular mils. Number 3/0 AWG has a circular mil area of 167,800 circular mils. Number 4/0 AWG has a circular mil area of 211,600 circular mils. 250 kc mil has a circular mil area of 250,000 circular mils. 300 kc mil has a circular mil area of 300,000 circular mils. 350 kc mil has a circular mil area of 350,000 circular mils. 400 kc mil has a circular mil area of 400,000 circular mils. 500 kc mil has a circular mil area of 500,000 circular mils. 600 kc mil has a circular mil area of 600,000 circular mils. 700 kc mil has a circular mil area of 700,000 circular mils. 750 kc mil has a circular mil area of 750,000 circular mils. 800 kc mil has a circular mil area of 800,000 circular mils. 900 kc mil has a circular mil area of 900,000 circular mils. 1000 kc mil has a circular mil area of 1 million circular mils. 1250 kc mill has a circular mill area of 1,250,000 circular mills. 1500 kc mill has a circular mill area of 1,500,000 circular mills. 1750 kc mill has a circular mill area of 1,750,000 circular mills. 2000 kc mill has a circular mill area of 2 million circular mills. Remember, these values are for copper conductors. Aluminum conductors will have different circular mill areas for the same AWG or kc mill size. Also, it's important to consult the NEC for the most up-to-date information on conductor sizes and ampacities. The information provided here is for educational purposes only and should not be used as a substitute for professional engineering advice. When dealing with electrical systems, always prioritize safety and consult with qualified professionals. Now let's delve deeper into some of the nuances of NEC section 250.122. This section specifically addresses the sizing of equipment grounding conductors for feeders. Feeders are the conductors that carry power from the service equipment, such as the main panel, to a sub-panel or a branch circuit distribution point. The equipment grounding conductor, often referred to as the EGC, is a critical safety component of the electrical system. It provides a low impedance path for fault current to flow back to the source, which allows the overcurrent protective device, such as a circuit breaker or fuse, to quickly open and clear the fault. This helps to prevent electrical shock hazards and minimize damage to equipment. As we discussed earlier, NEC section 250.122 provides a formula for calculating the minimum size of the equipment grounding conductor based on the size of the ungrounded conductors, also known as hot conductors. The basic principle is that the larger the hot conductors, the larger the equipment grounding conductor must be. This is because larger conductors are typically used to supply larger loads, which means that the potential fault current will also be higher. The 12.5% rule comes into play when the total cross-sectional area of the hot conductors exceeds 1100 kc mil. In this case, the equipment grounding conductor must have a cross-sectional area that is at least 12.5% of the total cross-sectional area of the hot conductors. This requirement is intended to ensure that the equipment grounding conductor has sufficient capacity to safely carry the fault current. It is important to note that this is just the minimum requirement. In some cases, it may be necessary to increase the size of the equipment grounding conductor to meet other requirements, such as voltage drop or coordination with overcurrent protective devices. For example, if the feeder is relatively long, the voltage drop on the equipment grounding conductor may be excessive if it is sized at the minimum requirement. In this case, it may be necessary to increase the size of the equipment grounding conductor to reduce the voltage drop and ensure that the equipment is operating properly. Similarly, if the equipment grounding conductor is not properly coordinated with the overcurrent protective devices, it may not be able to carry the fault current long enough for the overcurrent protective device to open. This could result in damage to the equipment or even an electrical shock hazard. In these cases, it may be necessary to increase the size of the equipment grounding conductor to improve coordination with the overcurrent protective devices. Another important consideration is the type of conductor used for the equipment grounding conductor. Copper and aluminum are the most common types of conductors used for electrical wiring. However, they have different electrical properties. Copper has a higher conductivity than aluminum, which means that it can carry more current for the same size conductor. As a result, a smaller copper conductor can often be used in place of a larger aluminum conductor. However, copper is also more expensive than aluminum. As a result, aluminum is often used for larger conductors to save money. When calculating the size of the equipment grounding conductor, it is important to use the correct circular mill area for the type of conductor being used. The NEC provides tables that list the circular mill areas for different sizes of copper and aluminum conductors. The grounding conductor can be bare or insulated. If it is insulated, the insulation must be green or green with one or more yellow stripes. This is to clearly identify the conductor as an equipment grounding conductor and prevent it from being used for any other purpose. The equipment grounding conductor must be properly connected to the equipment it is grounding. This is typically done by using a lug or connector that is specifically designed for grounding purposes. The connection must be tight and secure to ensure that there is a low impedance path for fault current to flow. It is also important to ensure that the equipment grounding conductor is properly protected from physical damage. This can be done by running the conductor in conduit or other protective raceway. In summary, NEC section 250.122 provides a formula for calculating the minimum size of the equipment grounding conductor for feeders based on the size of the hot conductors. The 12.5% rule comes into play when the total cross-sectional area of the hot conductors exceeds 1100 kcmil. In these cases, the equipment grounding conductor must have a cross-sectional area that is at least 12.5% of the total cross-sectional area of the hot conductors. However, this is just the minimum requirement. In some cases, it may be necessary to increase the size of the equipment grounding conductor to meet other requirements such as voltage drop or coordination with overcurrent protective devices. Always refer to the applicable codes and standards and consult with a qualified electrical engineer to determine the appropriate size of the equipment grounding conductor for a specific application. Now let's address a few more practical scenarios to solidify your understanding. Scenario 1: a large commercial building has a main service rated at 2000 amps. The main feeder conductors are 6 sets of 500 kcmil copper conductors per phase. What size copper equipment grounding conductor is required? Firstly, to determine the feeder current. The feeder current is 2000 amps, as stated in this scenario. Secondly, calculate the hot conductor area. We have 6 sets of 500 kcmil conductors, meaning 6 conductors multiplied by 500 kcmil per conductor, totaling 3000 kcmil. Thirdly, compare to 1100 kcmil. Since 3000 kcmil is significantly greater than 1100 kcmil, we proceed to step 4. Fourthly, calculate the grounding conductor area. The grounding conductor area is 0.125 multiplied by 3000 kcmil, which equals 375 kcmil. Fifthly, round up to standard size. Rounding up 375 kcmil, we find that a 400 kcmil copper conductor would be the appropriate minimum size for the equipment grounding conductor. Scenario 2: an industrial facility has a feeder supplying a critical motor load. The feeder is rated at 600 amps and uses 3 250 kcmil aluminum conductors per phase. What size aluminum equipment grounding conductor is needed? Firstly, determine the feeder current. The feeder current is 600 amps as given in the scenario. Secondly, calculate the hot conductor area. We have 3 conductors multiplied by 250 kcmil per conductor, totaling 750 kcmil. Thirdly, compare to 1100 kcmil. Since 750 kcmil is less than 1100 kcmil, we proceed to step 5. Fifthly, calculate the grounding conductor area. The grounding conductor area is 12.5% multiplied by 750 kcmil, which equals 93.75 kcmil. Sixthly, round up to standard size. Rounding up 93.75 kcmil, we find that a number 1/0 aluminum conductor with a circular mil area of approximately 105.6 kcmil would be the appropriate minimum size. These scenarios highlight the importance of following each step in the calculation to arrive at the correct equipment grounding conductor size. Remember to always consult the NEC and local codes for the most accurate and up-to-date requirements. Additional considerations for equipment grounding conductors include mechanical protection. The equipment grounding conductor must be protected from physical damage. This is typically achieved by installing it within a conduit or other approved raceway. The type of raceway required will depend on the specific application and the environment in which the conductor is installed. For example, in a corrosive environment, a corrosion-resistant raceway may be required. Also, the continuity of the grounding path should be maintained. The equipment grounding conductor must be continuous and electrically connected to all metal enclosures and equipment that it is intended to ground. This ensures that there is a low impedance path for fault current to flow back to the source. Proper bonding techniques must be used to ensure that all connections are tight and secure. Grounding electrode system connectivity is also a consideration. The equipment grounding conductor must be connected to the grounding electrode system. This system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. The grounding electrode system provides a connection to earth, which helps to stabilize the voltage and provide a path for fault current to dissipate. Ground fault protection of equipment, also known as GFP, is used in many electrical systems to provide additional protection against ground faults. GFP systems are designed to detect small ground faults and quickly trip the circuit breaker, minimizing the amount of damage that can occur. The equipment grounding conductor plays a critical role in GFP systems, providing a path for the fault current to flow back to the GFP sensor. Remember the importance of documentation. Accurate documentation of all grounding system components and connections is essential for proper maintenance and troubleshooting. This documentation should include the size and type of equipment grounding conductors, the location of all grounding electrodes, and the results of any ground impedance testing. Regular inspection and testing of the grounding system is also important to ensure that it is functioning properly. NEC Section 250 covers grounding and bonding requirements in detail. Familiarize yourself with this section of the code to ensure that you are following all applicable requirements. Local amendments to the NEC may also exist, so it is important to check with your local authority having jurisdiction to determine if there are any additional requirements in your area. Properly sized and installed equipment grounding conductors are essential for electrical safety. By following the requirements of the NEC and using good engineering practices, you can help to protect people and equipment from the hazards of electrical shock and fire. In summary, correctly determining the grounding conductor size per NEC Section 250.120 requires a systematic approach involving calculation of feeder current, determination of hot conductor area, comparison with the 1100 kcmil threshold, and application of the 12.5% rule when applicable. Rounding up to the nearest standard conductor size is crucial, and consulting the NEC tables for accurate circular mil areas is essential. Always consider additional factors such as mechanical protection, continuity, grounding electrode system connectivity, and ground fault protection. Accurate documentation and regular inspection are also vital for maintaining a safe and effective grounding system. By adhering to these guidelines and consulting with qualified professionals, you can ensure that your electrical systems are properly grounded and compliant with applicable codes and standards.